Okay, now if we want to be a bit more careful, we could take a look at how the chain ran and see if our starting value seem to skew the early iterations of the chain. Noticeably, we could throw out some of the initial iteration as brain. Okay, this part just explains why we need to check brain. Okay, so there is a code look at a bit closer look at the brain period. There is a function to plot the result. Okay, anyway, we can run it a little bit. Let's see what's in here. What are fancy things are here? Oh, okay. But it's not clear. We have to plot it one by one, right? Okay. Well, there is. It's not clear. Okay, so this is not good. Basically, okay. If we focus on the first 2,000 steps, I think that will be much more clear. Let's see. Yeah, it's still not clear. Basically, it actually tells you can see that the first 1,000 step is not stable, right? So that's why we need to look at this first 2,000 step to check the value of brain. Anyway, it's not clear here. And then okay, let's move on. So for example, suppose we look at plot of the iteration of the various parameters, and it looks as if the first few hundreds iterations may be noticeably influenced by our starting values. Then we might throw away the first 500 iterations like this. Okay, I choose 1,000, which is much more safe, but I think in our case, 500 is also okay, right? So here's the code, how we throw away the first 500. Okay, then after you throw away, you can rename after you throw away the brain part, right? We could rename our matrix called RES instead of the whole result matrix. So the RES, I believe, is simply just RES equals to results. You just throw away the first 1,000 columns of all 500 columns. I will throw away 1,000. So it's just something like this. Right? That's RES. Sorry, it should be row. It should be the row, not the column. Okay. So then, then I can rename like what I did here, right? We rename those because we don't really want the brain part. Okay. So this is histogram, and okay, we can calculate the probability that mu1 bigger than mu2 is this really big probability. So we call this posterior probability of mu1 minus mu2 bigger than 0 given all the data we observe. Okay, so after doing all that, there are some highlights of what we got. Okay, we got a big matrix. It's something like this times 4 matrix of results, where we call the results, and successive rows of the results matrix are successive states of the parameters of the Markov chain. And next one, okay, this is called the trace plot. Okay, the trace plot we just plot for each parameters to check the burn-in. That plot is called the trace plot. The trace plot for the 4 parameters, the first plot is for mu1, then sigma 1, then mu2, sigma 2, right? We can plot them and we can check the burn-in. Okay. Well, because the Markov chain is random, right? So every time you run your code, you will get a different result, but very similar because there's a randomness in it, right? Okay. And okay. What is our estimated posterior probability that mu1 minus mu2 bigger than 0? Okay, so in this run, the probability is 0.93, but in our run, it's 0.95. Okay, you see it's different because every time you run it, you actually get a slightly different result because there are randomness in it. But it should not too big difference. If you got really big difference in the two runs, then that means your markup chain did not converge at all. You need to run it longer. Okay, until your result becomes stable. So what if we want to change the prior? Okay, we don't know whether the prior actually affects our result really in a really significant manner, so we can try different prior. So we could try the whole thing again with improper uniform prior on everything. So the improper prior in our case is just you make the whole prior just proportional to 1. Okay, so simply by defining the prior density to be 1, okay, then that actually just means that your posterior is the same as your likelihood. So you can try it after class. Okay, so well, that's a bit of a complicated way to write 1, but we should return the answer 0 if either sigma 1 or sigma 2 is negative. Okay, we don't have time to explain why it's called improper, but this is a very popular prior actually. Usually, I would suggest you to use a proper prior. Just use the famous distribution that we learned, and to see, right? You can change. I would suggest you can change the prior parameters rather than make it improper, right? See, you can change those values. You can change 10 to 100, right? You can change 10 to 100 or 1000 or something like that, and to see what's going on here. Okay. And for trace plot, the mu1, sigma 1 looks okay because they're not obvious. They're not very obvious deviation from. The whole thing looks converged and stable. But in this run, the mu2 and the mu2 and sigma 2 seems occasionally will jump back at the end of MCMC. So if that's the case in your run, then you should try longer chain. Okay. Well, in this run, I think it looks okay. It didn't jump back at the end, but every time you run it, it can give you a different result, just because the randomness. Okay. So there's another code, and we can run it in a longer time. And let's see. Well, you can. Okay, how when you run, you can just run the markup chain continuously based on previous run, right? Just set starting value to the values at the end of the last chain. Then you run it. It's like you run another 10,000 steps of markup chain, right? Okay, and okay, I think that's all. Okay, this lecture notes are based on those references. Okay.